Pretty sure Darian's half made of salt with all the spits he's eaten today, though. Okay. Um. So let's say quick change here then. Let's make your assignment due on the end of Thursday. Is that fair? That way you still have kind of Friday as a little bit of time to ponder things as we need to. So the plan this week then is set of notes today, work day tomorrow. The stuff that we're doing on Wednesday will be kind of on the next assignment, and then work day, and then the following Monday we'll do quiz. So we'll just push your assignment back. So we'll make it Thursday. Okay, well, I understand that a couple of you guys got some extra help from Quan on. I understand that some of you guys got extra help from Quan on how to do a couple of the questions that involve compositions of functions last week. Yeah, so you really this is once you get the concept of how it works, I'm probably not going to be adding a whole lot to it. But let me give you an analogy of how I like to think of functions. I like the analogy of a vending machine. Okay, there's inputs and there's outputs because really that's what a function is. A function takes an input and gives you back an output. Like for example, the function y equals x plus 2. If I give you the input of 2, well, x plus 2, 2 plus 2 now gives you an output of 4. Does that make sense? And so everything has an input, x, and has an output. Well, either we read it as y or we read it as like f of x. Does that make sense so far? So a vending machine is a good analogy then because I put in money, that's my input, and I get back a chocolate bar. And if you like that machine analogy of put something in, get something out, that works. And then we've done a lot of things so far where we talk about, well, what if we need to add the outputs? What if we need to subtract the outputs? Because really that's what these are, right? F of x and g of x, those are the y output numbers for the same x input. Say that again. These notations right here are the y outputs. Different machines though, right? They each do something differently. Whatever you get out, we're going to add them, right? Let me try another analogy here. Let's say that Rebecca goes to a vending machine with $1 and she buys a juice box. Okay. But Abby goes to a different vending machine and she buys a chocolate bar. Well, they both input $1 because we're going to be consistent on what they input. Here, I'm asking you to add the two things they got back. So add a juice box and a chocolate bar. Here, subtract a juice box and a chocolate bar. Here, multiply them. Here, divide them. But here's the important thing. They each input $1. Right? The x has to be consistent. So if I each give them $1, if there's $1 right here, then this is what happens when they each buy something for $1. What if I give them $2? Well, if I give her $2, maybe she buys a bag of chips and a bottle of Sprite. You get what I'm saying here? So it has to be consistent. Whatever number you use for x right here, you have to use the same numbers right here. So this is just basically a task showing what we've done so far. Let's just try a couple of things here, because if we were to actually add, subtract, multiply, and divide all of these functions, it would take forever. So why don't we start by maybe adding these two functions to each other right here? If I were to add these to each other, what would we get? Well, is it really easy to add them at this particular moment in time? Nah, this guy right here, I should mess around with it, right? Let's make it x squared plus 4x plus 4. That's foiling it out, right? Then minus 5. So I really have x squared plus 4x minus 1. So if I were to take this one here and add it to that one there, add your like terms. What would we have left then? We'd have 4x squared. We'd have negative x minus 2. In this one here, I just said pretend we're adding. Which x value is this for? When x is 1 or 2 or 3? For all of them, right? This applies to every single x value, every single one across the board. And that's what an equation does, right? An equation written in this format means I don't know what x is, but this accounts for when x is 1 and 1.1 and 1.2 and 1.2005. Right? So this accounts for every single x value. What about if it's in a graphical format? I'll go down to this one here. What if I tried to add these values? Well, it's usually best to do it one at a time for each like x value. So let's pick an x value like 0. See how right here there's a 3 and -1 on the same like vertical plane. So 3 and -1, when we add them, let's just keep adding because it's simple. 3 and -1 would give you 2. And then unlike here where I'm doing it for all x values, on something like this, I literally have to test them like 1 point at a time. See how like this one here is a lot more broad, and this one here is very like 1 point at a time specific. So let's just keep doing the exercise. Here was a good spot. Right here's a good spot. Here I've got a point at 1, and here I've got a point at -5. Why didn't I pick the point in between? Yeah, exactly, right? Like, let's just pick points that I know I'm for sure on, something consistent, right? So 1 and -5, when we add them, would give us -4, which would go here. Right. Now, could I do this and do my best attempt at whatever this value is right here with that value right there? You see how I'm still being consistent with the x inputs? It's kind of tough because this one, well, actually, this one I'm pretty sure is at 2. But where exactly is that one? 4.5, 4.75. So usually I just do it for whole numbers. Actually, this one right here should work. There's a point there and a point there. So -1 and -5 is going to be -6. So I'm guessing that as I add them together, it probably would start fitting together like this. But am I actually going to do every single point along the way? That's ridiculous, right? But hopefully I made my point to you guys. Up here when we use equations, this does account for every single x value. When you do it point by point on a graph, you just have to do one at a time, right? The same thing you can do right here. You just literally you're adding them up. So like here, if x is -4, well then our y values when you add them gives you -2, and here it gives you -2, and actually this is really boring. Shouldn't have done add. Add was a poor example. I just want to make sure it's clear though. You're not going to take this 4 and add this -5. Does that make sense? That's not fair. Because here I gave Rebecca $2 as her input, and here I give Abby $3 as her input. It's not fair to add a 2 and a 3. That's adding apples and oranges, right? You have to add, if this y gets an input of 2, then what is this input plus this output and this output? It's got to be consistent. So, do you guys feel like you get the point I'm trying to make here? Yes, exactly. That's exactly how my analogies work. Okay. All right, let's skip through this here. Today what we're going to do is something called a composition of functions, where if you like my vending machine analogy where you have an input and it gives you an output, we're actually going to run things through more than one machine. And this actually makes a lot of intuitive sense in terms of how technology works. Most things are not simple machines. You guys ever heard of simple machines before, like a wedge, an inclined plane? You guys ever heard of some of those things before, like a pulley? Well, I mean, think of your car. Is there literally just one? Well, no, right? Because this moves this, which moves this, which moves this, which does that, right? Well, that same concept kind of applies here, is that we're going to take an input, we're going to put it into a function, and we're going to get an output. And then we're immediately going to take that and put it into another machine. And this is a composition of functions where it goes right from one to the next. So follow this example. I give you an input of 3. This machine squares it, so 3 squared gives you 9. But we're not done, right? Because we're not talking about like one-off simple machines. We're talking about something complicated which has like 2 steps to it, or 3 steps, or 4 steps, right? So now that we've got 9, well, 9 is now a new input, and we're going to put it into the function x plus 1. Well, so 9 plus 1 now gives you 10. And this is the way we would notate this. We took an x value, we put it in to the F machine, and when we were done putting it into the F machine, we then put it into the G machine. the real link here is that whatever you get as an output right here immediately becomes your new input right here. Here's the analogy I like for this. I know it's not fantastic, but I think I told one of you this before. Imagine you're in the States and you want to go buy something at a vending machine, but you only have Canadian money, and you need American money to put into the machine, right? You try to put the Canadian money into the machine, doesn't work. So the first thing you do is you go take your Canadian money and you go to the bank and you change your Canadian money out for American money. Now you take your American money and go buy something with it. You see how there's like a two-step link to it? In Canada, I just take my money and I go buy something. But in the States, Canadian money converts to American money. That's the first change. Then American money lets you buy something. That's what this kind of concept involves. So from here to here, and then from here to here. And you can actually do this like a million times, right? You could have A go to B, B go to C, C go to D, D go to E. And hopefully you guys can kind of appreciate that this sort of notation and concept, like this is actually real world stuff, right? Because nothing is just a one-step problem, right? Often you have to have 5, 6 steps in a process. Well, if that process is mathematical, this is a good way of illustrating it. So let's try this example here. Let's say that I tell you that f of x is 3x plus 4, and then g of x is 5x minus 6. What we want to figure out is what happens right here, where what you're doing is you're taking the g of x function and you're putting it inside f of x. I want to pause for a second. What is a function? I found this Dr. Seussy looking picture on there. Isn't a function written as f of x? Isn't that the way we write it? What does this notation mean? Well, this notation means that we have an unknown x, right? We don't know what this x number could be. It could be 1, it could be 2, it could be 3. And what we're going to do is we're going to plug a number in for x and tell you what y is. So if you plug in 1, 1 might give you 3. If you plug in 2, 2 might give you 5. 3 might give you 7. And eventually we say, well, what if you plug in an unknown number? Well, if you plug in an unknown number, you get 2 times that unknown number plus 1, and you get an equation. Does that make sense? Well, what happens when we want you to plug in a number, but rather than plugging in a number, I want you to plug an equation into an equation. So I don't want you to plug a number into an equation. I want you to plug an equation into an equation. Here's how this would look. This notation right here means that the g of x is actually what's inside your f of x. So we're going to take this whole equation and we're going to replace it into that one variable right there. And when we're done, we're going to have 3. Now, it used to be 3x plus 4, but now it's 3 g of x's plus 4. See how g of x is now in that location? But let's not write it as g of x. Let's write it as, I got to go this way, so I'm not locking room here. Write it as 3 5x minus 6 plus 4. See how this entire equation took the place of that variable? Normally when we work with functions, a number takes the place of x. Right? If x is 1, what's 2? Well, what's the equation? If x is 2, what's the equation? Well, what we're doing here now is we're taking an equation and putting it in its spot. So now you actually have to do 2 things. Now if I want to figure out what the value is, I have to figure out what x is right here. I have to put it into this bracketed equation right here. And then once I figure out what this bracketed equation is right here, then I can put it into the big equation. See how that's kind of a 2-step system here? So first you do the inside equation, then you do like the big equation part. So let me try some examples. This often works better once we actually try something. So maybe a last point before I get there. Just the visual of apples turning into lemons and then lemons turning into oranges. We're going to take this equation, plug it into here, and then we're going to take that equation and plug it into here. We're going to mix equations into each other now. So, all right, let's try this one here. I'm going to give you 3 equations, and we're going to start off simple, and then by the time we get to f, which is like ridiculous, because I'm just being stupid, hopefully you guys will get the concept. So let's start with the first one here. What am I asking you to do in this first equation right here? Like put it into people words. What do I want as an equation here? We want to take x, an unknown value, and we want to put it inside the g equation. But then we want to take that entire g equation and make it our variable for the f equation. So what is our f equation? Well, the f equation is supposed to be 4x. That's what it's supposed to be, right? But I don't want 4x's. What I really want is 4 g of x's. You get what I'm saying here? F of x is 4x. F of gx means that it's 4 g of x's. But what is g of x? Well, g of x was x plus 6. So my final equation now is 4x plus 24. Lost you. Okay. Here, let me try highlighting something so this makes sense. This x right here means that we don't know what number we're going to use. And because of that, it gives us this x right here. Well, likewise right here, this g of x right here is kind of our unknown variable. Well, if the x goes here and here, then the g of x goes here and here, but it still gets multiplied by 4. Like essentially what this machine does is it says, take any number and multiply it by 4. Right? That's what the equation does. Only this guy right here doesn't say take any number and multiply it by 4. It means take my equation and multiply it by 4. Let me try the next one. I'm sure you guys are already ahead of me. This one right here, I'd figure out what g of x is. G of x is normally supposed to be x plus 6. But now I want it to be h of x in its spot. So then h of x is going to be x squared plus 6. You see how this x squared is taking the place of that x right there? Okay, C. What if I don't make it x? What if I make it a number? Well, it just means you're putting a number in when you're done. Right? Like, okay, what is h of x equation? H of x equation was supposed to be x squared. But I don't want x squared, I want f of 4. So what I should really do is make that f of 4 squared. Okay, well, what is the f equation? Well, the f equation was 4x. And now when I'm done, I want to still square that. But see how there's a 4 sitting right here? Unlike in the previous examples where I didn't know what x was, I do know what x is. X is 4. So I need 4 times 4 and then square it. 4 squared is 16. Square that again, 256. What's that? 16 squared? You guys able to follow that logic there? So unlike this one right here where there's an x when you're done, for this one right here, this 4 means when you're finished, replace this x with a 4. That's all. You can actually put a function back inside itself. Here, I want you to do x squared, right? The first h of x means to square it. But then when you put the x squared inside an x squared, that's really what you have, right? You have a something squared. That something is x squared. So when you're done, you actually have x to the 4. Or this one right here. This one was supposed to be x plus 6. But we're going to make it f of x, which is actually, this bit here is now 4x. But then the minus 3 means we'll actually make x minus 3. When I give you a number right here, what I'm really doing is we're looking for one answer rather than an equation. Some of these ones are still equations because, like right here, I don't know what x is, so I leave it as x to the 4. Right here, I still don't know what x is, so it's 4x plus 24. But in this one right here, I knew which x I was asking you about, so you should get a number. We can often write this as a coordinate point, by the way. You could tell me that if you input minus 3, you output minus 6. That's what a coordinate point does, right? The first part of the coordinate point, the x value, is what you input. And by the time we were finally done, the y value is your finished value. So you can write it as a coordinate point. Same thing with this one right here, by the way. You could have written it as, if you input 4, it'll eventually get you 256. It actually had to go through 2 machines, though, right? The 4 had to go into the F machine. And then after the 4 went into the F machine, it also went into the H machine. But by the time you were done, a 4 eventually turned into the 256. You guys get that concept? Okay, so try the last one if you haven't already beat me to it then. Because really, this is just exaggerating it to the point of ridiculous. But if you get it, you'll be able to solve it. You guys already tried this a little bit? I start with the G equation. The G equation is supposed to be something plus 6. So I'm just going to leave a big blank and call it something plus 6. That something inside is going to be the F equation. So the F equation was supposed to be 4x. But we're not going to make it x because we're going to put whatever the H equation was, which was x squared. But I'm still not even going to call that x because I actually want to put G in there. And G was something plus 6. And then finally, that something is F, which is 4x. You guys follow that train of thought there? Honestly, let's just leave it there. If we have to FOIL it out, though, you guys could FOIL it out, right? So this is many equations shoved inside of each other. Really, think of this backwards here. What am I asking you to do to x? In order, watch the reverse order. In order, I need for you to take x. I need you to multiply it by 4. That'd be the first thing you do by BEDMAS, right? Well, that's the f of x equation. Take a number, multiply by 4. Once you have that number multiplied by 4, then add 6 to it. Well, that's take a number and add 6 to it. That's the G equation. The next thing up would be h, which would be, you know how BEDMAS then means do your exponent next, then you have to square it. Well, h means take whatever number you have and square it. After we're done squaring it, the next thing we do is we would times by 4. Well, that's back to this f equation again, meaning times by 4. And then the last thing we need to do is add 6, which is the G equation, which is take whatever number you have and add 6. You see how really, when you guys were learning BEDMAS, you were actually learning composite functions. You were learning a whole bunch of small little pieces in a row, and order mattered. First times 4, then add 6, then square, then times by 4, then add 6. Now you're done. You were actually doing 5 things. These are the 5 things. This one, this one, this one, this one, and this one. I find that most students, when they struggle, they just need to know which way to go. Should you start on the inside and kind of work your way out? Or should you start on the outside and work your way in? And really, both can be done. You just need to pick a method that somehow works for you. So some kids like to start on the outside and say G, and they go something plus 6. Other kids like to kind of start in the middle and kind of work their way backwards. So. Anyways, that's the concept. You guys feel like you kind of have the basic idea of what we're going for? The bigger question now here is just, well, how can you be asked questions? So let's talk notation. One of the ways we'll write it is f bracket g bracket x, which really means that you have a g of x equation inside the f of x equation. The way you would read it out loud is you would say g of f of g of x. Like you would say f of g of x. That's kind of how you read it. Okay, I mean, you could read it as x composed with g. This is f composed with 3. This is f composed with x. This is f composed with g of x. All you're doing is you're making an equation with equations. Okay. This is another notation you might see, though. Okay. It's not a dot. It's an open circle. If you ever see f open circle gx, it does not mean multiply them. FOGX actually means put the G inside the F. So you got to be super careful. F dot G is not the same as F open circle G. It's silly that they made two notations be so close to each other. I don't know why, but well, you guys heard me say this in physics a lot. If we go back and change things, there's quite a few that would be like, All right, so let's try another example here. I'm going to give you two functions. One of them is x to the minus 1. The other one is negative x squared. This first little bit here. Okay, so g open circle f of x, what it means is take your g function and inside of it, put the f function. That's what this notation means. Take the f function, put it inside the g function. Okay, well, what's the g function? Well, the g function was supposed to be negative something squared. What's my something? X to the minus 1. Does that make sense? If you wanted to, you could have written it as negative f of x squared. Because really, this f of x right here means that wherever you have an x, put f of x. But that's what f of x is, x to the minus 1. Right? If I wanted to simplify this a bit more, you guys okay if I turn it into that? Because the negative 1 and the 2 multiply by each other. All right. One more way of writing it. What if I wrote it as this? You guys all familiar and remember how a negative exponent refers to the denominator of a fraction? You guys remember doing this? Here's the reason why I bring this one up. I didn't ask you in this example here what the final equation was. One of the ways that they might assess you, and I see this on the diploma every year, they might ask you a question like, well, what's the domain of this thing? Okay, so let's review what domain is. Sometimes you learn about domain being the x numbers and range is the y numbers. Maybe another way of thinking about it is x is your inputs. Your domain is your inputs. What input numbers can you use for x? Could I use 1 for x? Sure, why not? When I'm done, 1 over 1 squared, I can do that. Could x be 2? Could x be 3? Where am I going with this? What number can't x be? Yeah, does that make sense? So we could write this in a lot of different ways, but if I'm asking you what the domain is, basically I'm telling you that x can't be 0, right? Maybe you'd see it like this. X is an element of the reals. X can be any number you want it to be, but there is an exception. You can't use 0. And I like this because it actually fits with my vending machine analogy. Okay, not all inputs are possible. Say you go up to a vending machine with a loonie. Will it accept the loonie? Sure. Will it accept a toonie? Sure. Would it accept a Mexican, what do they use, pesos? I don't think a vending machine would accept a Mexican peso. You get what I'm saying here? So not every input is possible because not everything can actually fit inside a machine as like the starting value. You get what I'm saying here? This would be a good example of that. I can't use 0 because it's just not possible when I'm done. You get where I'm going here? While I'm talking about that, that actually works for range as well. Range, you guys remember range? Range is like your y values you'd get back. Range is your outputs. Not every equation has every output possible. Same thing with a vending machine. Can I go to a vending machine and buy a chocolate bar? Sure. A bag of chips? Sure. A motorcycle? Okay, no. Right. Not every output is also possible. Let me give you an example of that in a graphical format. You guys know a quadratic graph, right? Here's a quadratic graph. Is the output of 7 possible? Yeah, like way up here is 7, that's possible. Is the output of negative 2 possible? No, this graph never crosses negative 2. Right. With reciprocal graphs, which is kind of like what that one was right there, if you have an asymptote, the asymptote would be a good example of the non-permissible value. Could you ever input the number 0 here? No, physically it's not possible. What about the output of 0? It might not be possible either. Okay, let's try another one here. For this one here, we're actually working backwards. Rather than me tell you what the two starting functions are, here I'm going to tell you what the final function is, and I want you to figure out what the pieces were that made it. So it's kind of a different puzzle. I'm not going to tell you what A and B were to make C. I'm going to tell you what C is, and I'm going to ask you what pieces could make this function. So let's try the first one together here. I need to have two functions. One of them is f of x. One of them is g of x, where the g function was put inside the f function. So I'm going to take a stab at it. Which function is the inside function? The one that's been like replacing something? X minus 2, yeah. Right? Because you see how I've got two different x minus 2 sitting here, right? This used to be an x, right? Because it's supposed to be x squared plus x plus 1, but all of these x's right here and here have had an x minus 2 replace them. So working backwards, I'm just going to undo this. These are my two functions. This one right here was the original function, that this piece went in there. See how that works? Now that I've shown you guys the main concept, my bigger goal now is to try to expose you to as many types of puzzles and problems as you can, because that's what you're going to get on a diploma. They don't usually ask nice, simple questions. They ask really stupid, dumb questions. And so, like, this is just the reverse of what we did, right? And so I need you to be able to take the skills I've shown you and extrapolate and use them in whatever situation they come up with. What about here? You want to try this one here? What's a function that's like inside something else? That'll work, yeah. Why don't we make the x cubed plus 1 be the inside function? What was it put inside of then? Absolute value x plus 2. Yeah. You guys get this concept though, right? Okay. So that's another way you could get assessed is just work backwards. Darren. That'll work. There is more than one answer, yeah. On this one here, an alternate answer would be that one of them was, let's see, this one could have been the absolute value of x3 plus 1. No, that's not going to do it. I get what you're saying. There's another way you can do this, though. I think I just need to write them backwards. I need to start with this one here. Why don't I make one of them be x plus 2? There we go. And then this one is going to be this. See how that one works there? So the base is the x plus 2, and you're going to take this bit and put it in that location. Yeah. That's all I really did, right? Is I just changed where that was. There's more than one way you could have written it. Okay, let's try another type of question. What if I were to give you graphs? And I were to ask you to do a composition of functions. Could we do that? It's hard. It's possible, but it's hard. Now, everything we've been doing up till now, we've been doing in equation format. But in graphs and table of values, you literally have to do it one point at a time. It's tedious and it sucks. But I'm pretty sure you could do it. Let's pick an x value. Let's pick a value for x to start with. 0 is a good choice. Okay. Okay, let's take 0. Let's start on the inside here. What would g of 0 have been? If I did g of 0, I'm going to go to the g graph right here. And when g was 0 right here, see how it was minus 1? Does that make sense? So if I were to write it like this, f of g of 0, that would have been f of minus 1. Because g of 0 is minus 1. You get what I'm saying here? When I plug 0 into the g, right here, I get minus 1. But what is f of minus 1? Well, now I need to go to the blue graph, input minus 1, which is right here. What's the output? Correct. So when we're done, 0 eventually gave me negative 3. 0 originally gave us negative 1, and then after it gave us negative 1, it gave us negative 3. Let's do a few more examples. You'll be fine. Okay, let's try 1. So first we need to figure out what f of g of 1 would be. So what is g of 1? Go to your g graph and tell me what happens when you put a 1 in. 5. Looks like it's 0.5. Okay. Now we have to find what f of 0.5 is. Well, 0.5 is right here. I believe it's actually negative 1.5 because this is going up by 2s, hey? See how 0.5 would be right here vertically? I'm not drawing it in a straight line. I believe the y value here is at negative 1.5. Well, let's try 2. Maybe I'll try not to make it quite so busy here. What is g of 2? So go to the g graph, find 2. It's 0. Okay, so now 0 is now my new input. Go to the f graph. When f is 0, that would be right here, is where x is 0 now on that graph. And so its output is negative 2. One more, then we'll move on here. Let's try 3. G of 3 right here is 0.5. that right? G of 3 is 0.5. I think I screwed this one up here, actually. This was a negative 0.5. That's a negative. Negative 0.5 on this one here. Actually, that one wouldn't have been 1.5. That would have been 2.5. Yeah, I screwed up on a negative there. Sorry, I hope that didn't throw you guys off. Okay, 3 gives 0.5, and then 0.5 gives negative 1.5. One last one, just to make sure we're clear. 4. 4 gives 1, and then 1 gave negative 1. Is able to follow that? Equations are by far the easiest things to work with because you're literally doing it for the generic x. If you have to do it on a table of values or on a graph, it sucks. Because you literally got to do it point by point. Okay, let's skip this one here in the interest of time because I feel like you guys have the idea. No, I guess it's my last one. Can I do one more thing with you? I want to do a table of values because this is what's on your assignment. Let me give you some points. I'm just making up a new example. Okay, let's make this be f of x. Let's let this be g of x. All right, let's do this. Because I think this is what's on your assignment. Something that looks somewhat similar to this. All right, let's start simple here. I want you to tell me what f of 1 is. What does that mean? Okay. Well, I don't actually have on here. I get what you're saying because it's halfway in between here, but I didn't actually give you an input of 1 to work with. So this one's not possible. What if I give you f of 2? Yeah, right? Think input output. Can this machine accept a 2 input? Yep. What does it give you back? A 4 output. What if I were to give you f of g of 2? Okay, well, take 2, plug it into the g machine. So 2 gives 3. Then this 3, now it's this 3 up here that gives 1 though, right? Well, make sure you're careful. It's convenient that 3, 1 is on both. This 2 gave this 3 right here, and then this 3 gave that 1. Let's try another one. Let's do f of g of, no, it's not going to work, of 5. F of g of 5. So start with the 5. Put the 5 into the g equation. 5 gave 3. And then this 3 here gives 1. Let's try g of f of 2. So see how I changed the order this time though? Start with 2 as your input, plug it into the f equation. Well, no, because you got to start with the 2 and plug it into the right equation, right? So 2 needs to get plugged into the f equation. See how that works? So 2 gets plugged into the f equation, which 2 gives you 3, right? Which really means that now I want g of 3. 3 gives... I screwed up. Sorry, my bad. Ignore what I just said. I see what I did wrong. I did exactly what we were just doing. Start over. G of f of 2. Take 2, plug it into the f equation to give you 4, and then 4 gives you 0, so this is 0. Okay, one last one here. Let's do g of f of g of 2. Okay, well, it might not because not everything fits. 2 into g gives you 3. Then plug it into g again, gives you 1. But then you have to plug it into f. We didn't have a 1 for f. So sometimes, and think about computer code, this is where errors come in. is that I say, take this and make this, take this and make this, take this and make this. If any one step along the way is missing a little piece, the whole chain breaks down. You got what I'm saying here? So although we could plug 2 into here, and we could plug 2 into here, I don't have a 1 up here to work with, so something broke. You get what I'm saying? Right. Hopefully you can kind of appreciate how like the concepts, the big picture concepts behind this are very applicable to modern technology processing, right? Maybe you're not doing specifically this, but the concept behind multiple phases getting blurred into each other is. So, okay, I have 5 minutes before the bell goes here. Let's talk through your assignment. Tomorrow is meant to be work time. I actually do believe you guys will finish tomorrow, but I'll still push the assignment due date back till Thursday. I believe you. Okay. I have way too much. What? Okay, so first equation here. I've given you guys the table of values. What does this M4 now mean? Start with an input of 4 and start working backwards, right? So take 4, plug it into the F equation, then plug that into the G equation, and then plug that back into the F equation. You guys think you can do that one now? Okay. This one right here is what we were talking about as well. Take the J equation, put it inside the G equation, and then put that inside the F equation. Only this time it's in equation format. When you guys see this little notation right here, FOG, it means F bracket G bracket X. It's just another way of writing it. So this one here does FGX, this one does GFX. And all you're doing is 1 point at a time, seeing whether you can work them through. This next equation right here, I want you to graph 2 things. I want you to graph a quadratic. I want you to graph a linear equation. And then I want you to graph what happens when you put the linear equation inside of the quadratic equation. All that means is that this equation right here, this x right here, is actually an x plus 3. Then you square it. And this x right here is also an x plus 3. Right? So you just have a little bit more foiling to do. And then I won't answer this one for you here, but I want you to try to figure out how they're related. After they're graphed, I want you to look at the 2 graphs and see if you can see the similarities.
Sean, how do you do 4?
This one right here?
Yeah.
Just all parts, start at the beginning? Okay. So f minus g of x means for a consistent input, subtract their outputs. So like for example, here there's a 1, and here there's a 1, right? Subtract their y values. So what is this 1 right here minus this 2 right here give you? Yeah. Okay, so when you consistently started with a 1, you got -1 when you were done. Let's try the next number, 2. See how they both start with a 2? So what is 3 minus minus 4? So 2 will give you 7. 3 and 3 can be added. Now, see how this guy right here has a 0, though? And this guy right here does not have a 0? I can't add them together, because one of them is the number 0, and the other one does not have an input. And not having does not mean the number 0. That's different, right? Not existing is different than the number 0. So I would expect 1 comma something, 2 comma something, 3 comma something, and that's it. That works? Yeah. So I just said that one. This one right here is F bracket G bracket X. All right, let me talk through some on the back page here. This is a real-world scenario which you could kind of start using some of these concepts here. Let me just give you the analogy here. Let's say that you're a hamburger shop. You own Burger King or A&W or whatever, right? It's going to cost you $135 a day, let's say for your utilities and stuff like that. And it costs you $1.25 to make every hamburger, because that's how much it costs you to buy the ketchup, buy the bun, buy the burger, supposedly. Okay. Burgers get sold for $3.50 each. That's your profit. Okay. Could we write it? Whatever. Could we write some equations relating our costs and our revenue? Let's just try writing this one out here. So what are your costs? How do I write an equation for costs? And why don't I just use N, because N is how many hamburgers I sell. Right? So when I sell hamburgers, it costs me money because I have to pay for the stuff on them, right? So this is my cost function. Okay. Now, when I have cost, is that actually a good thing to me? No. Okay, this is negative in a way, right? This is bad. Now, the good news is that I make revenue. The way that I make revenue is that I charge $3.50 a hamburger. How do I write that equation? Well, let's just talk about what you put in the till, because you're getting ahead of me here. That's actually what this question right here is let's find Pn. Anyone want to take a stab as to what P I'm referring to for? Yeah, right? Because you have your costs, you have your revenue. How do you find your profit? Well, your profit is your costs minus your revenue, except I screwed that up, didn't I? Yeah, so if you guys want to make a quick change here, your profit should be revenue minus costs. Right? Which really just means take 350N and subtract 135 plus 1.25N. You guys kind of see how like this sort of concept could be used? I know it seems silly to do it in this way, but like the concept still fits. Okay. One more thing here though. It also asks for your maximum daily amount. Yeah. Now this is where that number comes in, because you know how these were N's right here? It really depends on how many hamburgers you sell. But I'm telling you that you can only sell as many as 3 hamburgers because then you run out of stuff, right? So now this is me illustrating the idea of up till now you were selling an unknown amount of hamburgers, but now I'm telling you, no, what happens if you sell 300, right? Because wouldn't that be how you make the most amount of money? Yeah, like you could say C of 300. That's really what I'm looking for, right? Oh, I think I'm really asking you for revenue. So C is cost. Do revenue there. Okay, I still have a couple minutes here. Let's keep talking through questions. This one right here is what we kind of just did, where I'm going to give you some graphs. Now, the good news here is I'm only doing it 1 point. So on this one right here, find me G of -1, and then after you find that, find F of that value. Okay. This one right here is different though. This one here says find your F value at 1, find your G value at 1, and divide them. Right? This one, you put something into the other function. This is literally just look at the graph and either divide or subtract the numbers from each other. Okay, last one. Okay, one last one here. We'll get there. Okay, tax season's coming around, and you've got to pay tax. But you're also going to put some money away for your retirement. And so here's what's going to happen. You're going to take $200 from every paycheck, and you're going to put it in, well, they take it off for you. They're going to put it into a retirement fund for you. Does that make sense? But another deduction that's going to happen is they're going to take off 29% tax, because that's what federal income tax is. But it makes a difference, because look at this right here. One of them... Just a reminder that the boys A and B we'll get there. Are practicing at WAA at 3:30. That's junior high A and B boys are practicing at 3:30 at WAA. Okay, I want you to look at the back part of the question here. This is F, then D, then X. Working backwards, X refers to how much money you made. Right? You made $100. No, you made $1,000 on the paycheck. Okay. D of X means first you take off the $200 deduction, and then you take off the 29%. But this one right here says first take off the 29%, then take off the 200. Do you see how that's slightly different? In one of them, it's deduction, then percentage. The other one, it's percentage and deduction. It actually makes a difference. So I want you to kind of like do an example right here and write a function for this, write a function for this, and then show me how they're different. Because in one case, you actually make more money than the other one. And honestly, this is what accountants do. Right? It's to try to figure out, well, let's try to lower this amount before we do this deduction because it's going to save you a few dollars here and there. So, okay, that's all I got. I think you guys actually will finish this tomorrow, and I'm available all day tomorrow to kind of work on it with you. So, okay, you guys can take off. It's 3:29.